Greetings, students, and welcome to our Synchronous session for week 3 of Chemistry B. I am your instructor, Mr. Sharan. This is for your actually asynchronous sessions, since there weren't any students in the sync session. So this is for you tuning in for the synchronous session and asynchronous session to work with. Sorry, I should say asynchronous. Um, you'll see on the screen there are two things currently. Currently, right now, there is a simulator program which we will be using. I'll be including links to this in the video notes and themselves, and in the comments to this YouTube video, and also in the announcement with the links itself. So I'd use those announcements. There's also a document that you're going to be using as well on reversible reactions. Bring that closer to the center for the moment. All right. This is going to look at the concept of chemical reactions, um, equilibrium that can be met at chemical reactions, and reactions that can go in both directions, reversible chemical reactions. We've touched upon this concept in the last week's session, where we were taking a look at just basic ideas of chemical reactions. But now we're going to take a little focus, a little more on the concept of specifically equilibrium. So, if you could, let's take a look at the documents in front of us. I'm scanning it up a little so we can. All right. So here we're going to be using once again reversible reactions, and we're going to be taking a look at reactants, products, looking at the transition states and the temperature. But we're specifically going to look at the reactants and products and how, starting with different configurations of reactants and products, could potentially affect our final outcome. Now, the question we are looking to answer is, for a known chemical reaction, one with known energy levels of the chemical transition state energy levels, a set temperature, and known starting products, what seems to be affecting this reaction? Is the reaction going to favor one of the products, or the one of the products or the reactants? Is it going to be pretty equal, or is it pretty random? So what we're going to do as part of this, and I'm going to do part of the data collection with you today. The rest of this you will need to complete on your own. So this is partially an outside lab assignment for you to complete as well. Uh, the main thing, as with all mine, the main score, though, however, will come from your final assessment quiz, which will also be posted with these video notes. So the same announcement you found this video link to, you'll also find the assessment link, which you should complete after you've conducted the lab. So after you've done this lab work and gone through this, then you should conduct it, and then you'll be able to take that. So let's start here. Okay, so we're going to be running 3 computer trials, and they're going to be at 300 seconds apiece. So that's about roughly 5 minutes of. That'll give us roughly about 5 minutes of time to measure these. We're going to go in 20-second intervals. So every 20 seconds, or roughly 20 seconds, we're going to take a reading of how much of the A molecule and the B molecule there is. We're then going to answer some questions, specifically which side of the reaction is favored, and there are more reactants. Are there more reactants or products for the experiment you set up? Why is that so? So we're going to get into that. And then we're going to graph concentrations as well. So we'll be doing A and B versus time. So here we'll end up using one of the two to help us out. But we were looking at the A and B versus time measurement and see how, as time progresses, these two change. We've got some final questions here. What is happening to the concentration at the beginning of the experiment? How does that differ from the happening at the end of the experiment? We're going to look at a vertical line on the graph where equilibrium is established. And we're going to take a look at all 3 trials, starting at different amounts. How does the final ratio of AP compare? So here's a couple of things, okay? So one of the questions that's asking here at the end, all 3 trials started at different amounts. How did the final ratio of A to B compare? All right. So here's the final ratio. So the final ratio we're looking for is A divided by B. What's that fraction? Simplified out. A divided by B. Now there's a couple of outcomes. The one where A, whichever one starts with more, could be favored in the reaction. There could be none of them favored, so it just depends on it's random. So there's no match. Regardless of what you start with, it could always be the same ratio. So like say A is always favored or B is always favored. Or it could be opposite effect. So we'll take a look at the possible effects here, but there's a few outcomes that we can look at. So let's get this set up. So I'm going to bring this back down a little so it's a little easier to manage and read. All right. Actually, you know what? I'm going to move this over a little, just a smidge. Now I'm keeping here. All right. Oops, let me see if I can move this over just a little more. All right, I think that's about as good as we're going to get. Okay, so let's get started on this assignment. And like I said, I'm going to run through some of this. I'm not going to do all of this for you. It is your responsibility to make sure that you've completed this on your own. But I do want to show you how much of this. So there's a couple of things. First off, 300. Okay, so let's take a look here. And you'll see I have an initial setup as well. 75 to 25 is my starting setup. So for my first one, I want to make sure it's set to 75 to 25. I have a stopwatch down here, which I've clicked start on. So that means as soon as I hit the play button, it'll start counting. So I've got my concentrations, and I've turned on the species information, species meaning the different types of molecules, here specifically so that for these two numbers, number of these actual molecules. Now the only thing left is to set our reaction rates. So I'm going to set it to this. I've moved the left bar to the 20 mark and the right bar to, actually I'm going to move it down. I want it to the 15 and the right bar to the 10. Okay. Now these are distance measurements. These aren't actual values, but this line here once again represents the activation energy. So this is the activation energy required to get particles on this type B to move over to A. And this is the activation energy required to get particles that are of the A type to become B. Oh, sorry, the B type to become A. And this is for A type to become B. So we'll see that there's a higher energy need on this side than there is on this side for change. Now, let's see what the effect of that is. So I'm going to start collecting data and we'll see where it goes from there. All right, you can see my particles. And you'll notice as the particles jump to the other side. All right, so I actually missed my cutoff, but at 30, oops. All right, so I'm going to reset this actually. So we had this kind of not work the way we wanted to. So we're going to reset this and try this again. All right, so, and oops, sorry. So this time I need to hit the 20. And I'm going to try the best I can to get the 20 mark. I'm not going to get it exactly, so as soon as I see 19, I'm going to click it. So I'll get a little close to 19, maybe a little over 20. All right, so first one, I've got 71 to 29. Let's take a look at the next one. So let's keep going. I want to get 40 seconds. Nope. Oh, I overshot 44. Well, I'm going to get it anyway, even though I did an overshoot. So I may have a little time off. So I'm going to put the number in just because I overshot. Since we are going to be doing graphing later, it is important that we get as close as we can. So 60 is the next one I need. All right, so that's pretty close. That'll round. So we've got 63, 37. Let's go to the next one, 80. A little overshot again, but this time 64, 36. All right, so seeing some fluctuation. Seems to go a little back and forth. All right, for 100 seconds, or a little over 100 seconds and change. 61.39. All right, and we're going to continue. So I'm going to get I want to get here the full set of data. So I'm going to keep collecting until I get a final. So we're going to get to 120 and stop. So 120 is 56.44. So it definitely seems to be moving in a direction. Let's keep going. All right, for 140, we've got 54.46. So, 160, a little over, so I almost got 162. So, 53.47. Since I went over more than one, I'm going to put in a quick reminder here. 161.94. That way I know that where this was. I'm typing these in. You might want to, if you can, print this so that it's a lot easier to deal with. All right, let's keep going. I need 180 now. Oops, a little bit of an overshot there as well. 53.47. Oh, so we're getting a bit of a repeat. So this might be actually where we're starting to hit that balance and equilibrium. All right, let's go 200. 53. So we definitely seem to be hitting a. We definitely seem to be at this point hitting a sort of pattern, if you will. Let's try 220. 53.47. So we can continue this, but it definitely seems to be. We're definitely starting to get a reaction. So it looks like with the current setup, at about 160 seconds, we're starting to hit equilibrium, and it's pretty much staying as is. We'll verify that though. Let's just take a few more data points. Okay, here we go. So we definitely can see it's slowed. Let's keep going. To 59.58, that's about as close as I'm going to get. 47.53. Okay, so kept going. So we did get 53.47 is definitely going to be probably our equilibrium point. That's a point where it was the most stable. But as time progressed, it kept going. 280. All right, noticing it. 47.53. And then finally to 300. 47.53. All right. Okay, so final ratio 47 to 53. We're not really gonna. Those are both prime numbers, so we're not going to be reducing that too much. We could divide it out as a decimal, so their decimal as a ratio, 47 to 53, gives me at about an 88% ratio. So we seem to have a 0.88 ratio. All right. Now the question is, with new settings on the other side, what'll this be? So the new settings for trial 2. Okay, so trial 2 we did 75, 25. Now we want to, as part of the instructions, okay, so start with different amounts of A and B for each trial. So they should not be the same value. So while I'm tempted to try 50-50, I don't really want to do that because I want there to be um, a good balance. So for this one, I'm going to choose 25, 75. And the question is, are we going to get the same ratio at the end, or are we going to get a different one? So I'd want to set this to 2. Oh, pause that. Reset. Start. 25 to 75. And we'll start collecting again. Now, I'm not going to go too much longer on the video. I only have about 10 more minutes of time to go with, but we're going to take a few more pieces of data, and then I'll talk a little about the graphing and what you'll need to do. I will base, once again, our final on the assessment of this on how you perform on this and some of the findings that we should come out of this. All right, so let's get this started. So I'm now flipped it. There's more B than A to start with. All right, so 25 to 75 after 20 seconds. Let's see, we're going to 40 seconds. All right, oops, still a bit of an overshoot. We got 24 to 76. Not too much of a shift yet. All right, let's keep going. Okay, 24 to 76. So we can keep going, but so far what we're seeing is at this temperature, with these concentrations, we get very little reaction. So this is a point where there's not either enough reactants to push this reaction forward, or maybe the temperature's not high enough. It does take a lot more energy to transform 20 A's into B's for that chemical reaction to go from A to B than it takes from go B to A. So this will depend a lot on what our starting temperature is, but let's keep going. All right, yep, 25 to 75. Okay, so I think we could probably pretty safely. Well, let's not say this. Take a look. We do have the temperature does fluctuate. 24, 76, and so on. All right. So, like I said, I'm pretty sure we're going to see if we keep running this, we're going to see the basic same pattern that we've seen so far. Okay, 25 to 75. All right. So if we go with this, it looks like 25 to 75 is our ratio. Now that one does reduce, so we have a ratio of 1 to 3. All right. So We have a ratio of 25 to 75 or a 1 to 3 ratio. All right, final part of the experiment. This one I leave up to you. Okay, so we've done 75 to 25, 25 to 75. Pick another configuration of A to B, and we're looking for what's the final A to B ratio. So one I might recommend is let's try 60 to 40. Okay, so this is a place where I think we could get a a nice range to see what differences we get. So if we were doing this last one, I'm going to recommend for this last one a range of 60-40, and we'll go from there. Now, for the graphing portion, so I want to take a look at the graphing portion of this. Let me zoom in so we can see this a little better. Oops. So for the graphing portion, on your graph, I want you to keep in mind that you're going to have an x and y axes on the graph. Your x-axis should be time, and you should just draw at the 20. So we've got 20, 40, 60, 80, 100, up to 300 seconds. And then on the y-axis, we should put your concentrations. Now remember, we're only up to 100 molecules, so you can scale this out as best you can. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Oh, perfect. 21, 22, 23, 24, 25, 25. That means everyone could be 4, and you'd get to 100, and that'd give you a nice range. So 0 to 100. So from this bottom line to the top line, 0 to 100, goes up by 4s, then coming across. I believe it's longer this way, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 14, 15, 16, 17, 19, 20, 21, 22, 23, 24, 25. On this final one, there's 25. You have 300 seconds in 20-second intervals. That's 15. You have 25. You have plenty of them. So you have plenty of room across on the bottom to work with those. All right, so you should graph this. You should get 2 lines. So just pick one of your trials to graph. Whichever trial, I would probably do not trial 2 since we are seeing that there's no real change. I do trial 1 or trial 3 with the current setup. And what we're going to be looking for is the equilibrium point. We're going to be looking at the point where they cross each other in the concentrations, or as we graph it, we should also be looking at places where pretty much change stop happening, where they're balanced out. Equilibrium doesn't necessarily mean there's equal quantities. Equilibrium in this case, what we're really looking for is the idea that chemical equilibrium is a point where the energy requirements of all have been met, and whatever chemical reactions are still occurring aren't upsetting the balance of ratios between the reactants and the products. So when we're at equilibrium, there could be still individual chemical reactions by individual molecules, but as a whole, the process has come to a balance and a stop where going in one direction and coming in the other are at the same rate, so it's as if there's no change. All right, so once again, check your course announcements. Same place you found the link to watch this video. From those course announcements, I want you to make sure that you've downloaded and done the work on this note sheet. Use the simulator link that I'm going to provide in the course announcements, and finally gone to the the session assessment and taken that at the end. That will be part of how I determine your final grade. So thanks for tuning in to this episode. Thanks for tuning in to this session and watching this video. Hopefully it will help you better understand the concepts of chemical reactions and chemical equilibrium.